This class is going to look at the history of the atom, and this is the person who put the theory of the atom into a scientific context. This is John Dalton, a chemistry teacher. Atoms had been proposed before him. However, before then it was purely philosophical. Dalton put the atomic theory on a scientific basis, on a way which could be tested empirically. And that's what made the difference between his theory of the atom and that, for example, of the ancient Greeks. The idea that we can test it scientifically. So, what objectives are we going to be looking at today? Well, we're going to discuss the process of theoretical change with respect to Dalton's atomic theory. We're going to look at the postulates of Dalton's atomic theory and the modifications of the theory. Mention the criteria that are considered when theories are accepted. For example, fit between evidence and theoretical constructs, reliability and accuracy of data, replicability of experiments, and consensus within the scientific community, and societal factors. So, further on, we're going to describe the structure of the atom and define the following terms: mass number, isotopes, and relative atomic masses based on the carbon-12 scale. So, the first point is that Dalton proposed the atomic theory to explain Chauve's law of constant proportions. And that law states that all substances combine in constant proportions. For example, they'll get the same amount of nitrogen combining the same amount of hydrogen to form ammonia, and it's always combined in the same proportion. And Dalton proposed a theory to explain that law. And there's some important things we need to say about a theory when we use it scientifically, because scientifically a theory has a different meaning to how we use it in everyday terms. So when scientists use the word theory, it has a different meaning from normal everyday use. In science, a theory is not a guess or a hunch. It is well substantiated, well supported, well documented explanation for our observations. Some people think that in science you have a theory and once it's proven it becomes a law. That's not how it works. A theory never becomes a law. Theories explain laws. And really in science, theories are far more important than the laws that they explain, because they can be applied to different areas. So theories are far more useful than laws are. So basically, a theory explains why phenomena occur, whereas a law will describe what happens, describe what phenomena happen. They overlap with repeated successful predictions. Laws make predictions, and scientific theories make predictions, and we can test them. And in fact, the idea of scientific theories is to perform experiments to find out if the prediction always works. And if it doesn't, it means your theory has to be modified. So science works by falsification, not proving. We can prove a theory to be false. We can never really prove a theory to be true. So what's the difference then, between a scientific theory and a law? Well, theories provide the best explanation of observations or events. And by best, really, we're normally talking about most economical. You might have heard of Ptolemy's model of the universe, where everything rotated around the Earth. That was one model of the universe, of the solar system. It was replaced by a Copernican one, when everything rotated around the sun. And this made a better explanation because it was more economical. It's something called Occam's razor, where the most economical explanation for a phenomenon is usually the best. It doesn't have to be, but that is usually the case. So a theory is the best explanation of observations or events, and normally this means the most economical. Whereas a law is a statement or equation that reliably predicts patterns or events in nature. So a theory is far more important. Also, a theory attempts to explain how or why something happens, whereas law is considered universally true, so it doesn't answer the why question. And by why, we really mean how come rather than what for. Science explains really how come questions really rather than what for, because why can be how come or what for. So theories are more complex than laws and contain several hypotheses, whereas a law is usually based on one well-supported hypothesis that states that something will happen. So examples of theories, then you have cell theory, Darwin's theory of evolution, Aparin's theory of chemical evolution, Einstein's theory of relativity. And let us take the first statement of cell theory. All organisms are made up of cells. That's the cell theory. A law like Newton's law of motion, Boyle's law, Mendelian's law of inheritance, Charles' law, Hardy-Weinberg's law. So Newton's law of motion states an object remains at rest unless acted upon by a force. An object in motion remains in motion and at constant velocity unless acted on by a force. That's a law. Scientific theories are best explanations of observations and are based on a large body of scientific evidence. Even valid predictions have been scientifically tested in many ways. The statement that all organisms are made of cells is based on numerous repeated observations under a microscope. A law is a universally accepted fact, statement, or equation capable of making reliable predictions. Or a law describes what nature does under certain conditions. Theories are explanations of phenomena, and laws are generalizations about a phenomenon. Theories explain how nature works, whereas laws explain what nature is doing under certain conditions. And theories are often descriptive and complex than laws, with detailed explanation contain several supported hypotheses, as a law is a concise summary of a large number of facts. Scientific study, however, is guided by societal constructs, which construct goals and values from which scientific research can be constructed. So notice society has certain goals and values, and this goes on to negotiation of salience, credibility, and legitimacy. So certain aspects of scientific knowledge depend on input from goals and values. although the thing is kind of diffuse. So moving on then to look at Count's law of definite proportions. Um, Different samples of the same compound always contain elements in the same proportion by mass, regardless where they come from. So example, samples of carbon dioxide obtained from different sources contain exactly the same ratio of mass of carbon to oxygen. And the mass ratio is 0.375. The relative numbers of atoms of each element in the given compound is always the same. For example, carbon dioxide, the gas obtained from different sources, contain exactly the same ratio of carbon atom to oxygen atom. And I said, no, the Count's law simply describes what happens, namely that elements act in constant proportions. It can be tested empirically, i.e. by experiment. Count's law was thoroughly tested, and the scientific community found it was valid. People tried to test it many times to see if they could find exceptions, but it always seemed valid. But it does not explain why these observations occur, and to explain why you need a theory. So Dalton proposed the atomic theory to explain Count's law, and Dalton had four postulates. Number one, elements are composed of small indivisible particles called atoms, and atoms of the same element are identical, and atoms of different elements are different. Atoms of different elements combine together in simple proportions to create a compound, and they'll always combine in these simple proportions. In a chemical reaction, atoms are rearranged, but not changed. In other words, one element can't change into another. Lead can't change into gold, for example. So we have those four postulates. It's important you know these postulates because naming them is often part of CAPE exams. And I say note that Dalton proposed the existence of atoms to explain a well-established law by giving atoms specific characteristics. And from that, the law of constant proportions can be explained. However, by giving these atoms specified properties, it enables scientists to carry out further tests. And from a scientific perspective, it seems that the theories are more important than laws. Dalton's atomic theory could be tested, however. Are atoms indestructible? Can we measure their masses? Things such as that. And the idea that atoms were indivisible, was challenged by J.J. Thomson through his experiment with a cathode ray tube. Notice we have a negative electrode here, which is a cathode, and a positive electrode here, which is anode. And when you have a high voltage, cathode rays will go from the cathode to the anode. The point is, where do these particles come from? And J.J. Thomson said they must come from the atoms themselves. And since moving towards a positive terminal, they must be negatively charged. And notice, I suppose, as well as a high voltage, we need to have a low pressure so that the atoms of gas will not interact with the electrons. And what you get is a green glow, because electrons sometimes go onto the sides of the tube. Thomson proves that the green glow was observed as a consequence of negatively charged particles found within the atom itself. These particles must be negatively charged because they're attracted to a positive plate. And therefore Thomson proposed a plum pudding model of an atom. We could easily call it a chocolate chip model, where you have plums or chocolate chips embedded in a inert matrix, which is positively charged. So note that in Thomson model, there is a positively charged C, and there are no discrete positively charged particles. We just have an overall positively charged. The matrix has a positive charge. And this was called the plum pudding model. And these electrons are also hypothetical constructs used to explain cathode rays. At this time, we didn't know they were particles. And we've done further experiments which show they are, such as the Mulliken's experiment. But we're not going to go into that. But the plum pudding model was later challenged by the Geiger-Marsden experiment. But this is more or less showing what a plum pudding. This is a plum pudding. These are the plums, I guess, and this is the matrix for pudding. So plums in the plum pudding is analogous to electrons in an atom. So they're more or less the same. But this was challenged by the Geiger-Marsden experiment, which is shown here, where you have a source of alpha particles. We knew about alpha particles. And we put a sheet of gold foil around a fluorescent screen. And the particles, it was noted, can move in several different directions. Some of them went through directly, some went through at an angle, some were widely deflected, and some almost bounced back. And this told us about the structure of an atom. In Thomson's model, it was expected for all of the alpha particles to move straight through the gold foil. But in Rutherford's model, here's the atom. Most will pass straight through it. Some are slightly deflected, and some are largely deflected. And what this means is most of the mass of the atom is in a concentrated region in the center. And therefore, most of an atom is empty space, more or less. So, if you could increase the size of an atom to, say, the National Arena, the nucleus would simply be a ping pong ball in the middle of the National Stadium, and the outer seats should have your electrons. As you can see, most of the atom is simply empty space. So Rutherford proposed the structure of an atom shown on the left. Notice protons have not yet been discovered, so the nucleus is simply a positively charged mass. And the proposition of the Plumford model has been given on the basis that it could be tested and consequently modified. One thing I needed to emphasize really was that it also shows that most of the atom is empty space. So protons were discovered later. In 1917, Rutherford proved that the hydrogen nucleus is present in other nuclei as a result described as the discovery of the proton. He noticed that when alpha particles were shot into nitrogen gas, its scintillation detectors shown the signatures of hydrogen nuclei. Rutherford determined that the hydrogen could only have come from the nitrogen, and therefore nitrogen must contain hydrogen nuclei, and the hydrogen nucleus is therefore present in other nuclei as an elementary particle, which Rutherford named the proton, and the neuter, singular the Greek word for first. He found that protons at a mass of 1,836 times as great as the mass of an electron. So you can bombard an alpha particle into a nitrogen, and you get oxygen and a proton or hydrogen atom coming up. We'll come and discuss balancing nuclear reactions later, but you need to know how to do it. Notice the total number of particles is the same. 14 plus 4 is 18, 17 plus 1 is 18. And these must also, 7 plus 2 must be equal to 8 plus 1. And therefore that P could have been written as an H. Chadwick smashed alpha particles into beryllium, a rare metallic element, and allowed the radiation that was released to hit another target, paraffin wax. The experiment result showed a collision with beryllium atoms would release a massive neutral particles, which Chadwick named neutrons. And the point is, neutrons were specifically looked for. We knew basically that neutrons had to exist. So the behavioral beams of a proton, neutron, and electron in a field. We know that protons are going to be attracted to the negatively charged plate, and electrons to the positively charged plate. And note electrons are deflected much more than protons are, because it has a much smaller mass. This is a key part. Electrons are deflected towards the anode. They have the lowest mass and are therefore most deflected. Neutrons are not deflected at all because they have no charge. And protons are deflected towards the cathode because they are positively charged. They are less deflected than electrons because they have a greater mass. And the behavior of the subatomic particles in an electric field proves evidence of their charge and behavior. So we can move on to atomic weight and atomic mass. Atomic mass is the number of protons and neutrons in a single atom. Atomic weight is the weighted average of the atomic masses of all natural isotopes in an element. So atomic weight is the weighted average when all the natural isotopes are taken into account. So actually the mass of carbon-12 is in fact 12.0107, and that is due to the presence of a small amounts of carbon-13 and 14. And nucleides with the same atomic number but different mass numbers are called isotopes. And isotopes tend to be less stable and can have significantly different nuclear properties. But the chemical properties are going to be the same. So carbon-14 is one of the isotopes of carbon-12. It's not the major isotope. The major isotope is carbon-13, but carbon-14 is radioactive. So the mass number indicates 2 extra neutrons, and atomic number indicates it's still carbon. So carbon-14 is an important isotope used for radioactive carbon dating. And in order to find the relative atomic mass, we're going to multiply the percentage of each isotope by its atomic mass, and then divide by 100. And atomic masses has a mass of something like 13.5 AMU, where AMU stands for atomic mass units. And note the isotopic masses of carbon. Chlorine 35 is 35 exactly, and the mass of chlorine 37 is 37 exactly. And that more or less finishes this first theory class. So we can stop at this point.